Cool. Let's get started. We're going to do some do now notes, and then I'm going to check on the OSHA certification people to make sure they have a goal. All right. Today's do now question, I want you to draw the following two molecules. It's a nice refresher on if you can name and draw, and it also sets us up for our first section of today's lesson. So, first thing that I've asked you to make is propan-on. So, using our rulings, let me figure out, there we go. I'll write down the words. Propan-on, I think that's how it was spelled, or maybe I put an extra N in there. Yep, I have. So, again, when we're looking at organic chemistry, we have to break it down into the two components so that we can figure out the number of carbons and the functional group. So, prop tells me 3 carbons, and then the ending here, on, tells me that you have a ketone. Now, since this is only 3 carbons in length, it automatically tells us where the ketone is, because it can only be in one spot. So 1, 2, 3, double bonded oxygen has to go on carbon number 2, because if it's on carbon 1 or 3, it is now an aldehyde. So double bonded oxygen, and then we got to fill in our hydrogens to make sure that the carbons all have 4 bonds. So this carbon here is going to be CH3. This carbon has 1, 2, 3, 4 already, so it's fine. And then that's going to be CH3 as well. I don't like how they're so far apart, but it is what it is. Maybe I'll do that to make it look like it's okay. All right, propan-1. Got it? All right, next one that was on there is a little bit trickier because we're now dealing with our esters. We are dealing with ethyl propanoate. Yes. All right, going back here. So, this case, when we're looking at our suffix, the O8 ending tells me we have an ester. And so since I have an ester, I then know there must be 2 components to that ester. Just as a reminder of what we're looking at for an ester functional group, it is C double bond O with a single bond to an oxygen. So that is our little bit that we're looking at for our function group. Are we good? All right. This bit here, let me get another color, tells me number of carbons that are apart from the carboxylic acid half of the molecule. This here tells me number of carbons in the alcohol half of the molecule. That's why it is ethyl propanoate. So this component here, the C double bond O, that has come from my carboxylic acid component. I need 3. This counts as 1, so I need to do 2 more carbons. Are we good so far with that? Yes, Caleb. Question. No, I saw a confused face. Explain to me what you're confused on. You can draw it either way. So let me draw it this way, and then I can show you how you draw it the other way. It doesn't matter the orientation if I put the ethyl component first when I draw it or not. It's still the same molecule. So let me show you what I mean. I'll finish the molecule first. All right, so that's that guy, and then this guy over here is my ethyl for my for my alcohol. So that is my O from the OH. That's CH2, that's CH3. Let me finish in the hydrogens. All right, ethyl propanoate. You can draw it the other way around. That's what Caleb was kind of like, why are you drawing it with the carboxylic acid first? It doesn't matter. You could draw it this way around if you want. It's still the same molecule. Is this what you're referring to, Caleb? Okay. So that's the same molecule as that. The reason why they're the same molecule is that this carboxylic acid is still 1, 2, 3, and the alcohol component is still 1, 2. So you can draw it either of those 2 ways, and you still have the right answer. Now, if you had swapped the number of carbons around, let me show you the wrong answer. So if you did C double bond O, O, CH3, CH2, CH2, CH3, if you drew this, which is what Caleb might have drawn, this is not ethyl propanoate, this is propyl. ethanoate. See how it's the other way around now? Because when we're looking at this bit here is 2 carbons. That is the carboxylic acid. And this here is 3 carbons from the alcohol. So it does matter how many carbons you're attaching to each side. Doesn't matter what order you put them in, but the number of carbons is what the important thing is. Yes? So what you need to look at is, here's my C double bond O with the O, like that. So the one with the C double bond O, that is the derivative from the carboxylic acid component. And that's 1, 2, 3, which is coming from this part of the name. So the carboxylic acid would have been propanoic acid. This bit here with the single bonded oxygen, that's coming from the alcohol. So that's coming from the ethanol. So that's one way you can draw it. This is also another way to draw it. Because if you cover this up, this is still the carboxylic acid component with the 3 carbons. That's still the ethanol with the 2 carbons. Yeah? This one, which is what Caleb sounds like he did, is the other way around. So if I cover this up, that's only 2 carbons. So that is ethanoic acid now. And this one, if you cover it up, that's single bonded oxygen. That's from the alcohol. That is 3 carbons. So that's propanol. All right? So you see how which way around you got to do it. It's good that you're learning the esters now, because it's going to make it easier when we do actually learn more about esters. All right, questions, concerns, or comments at this point? We're okay? All right. So the reason why I asked you to do these 2 molecules in particular is because, so we've drawn our molecules. Let's move on to the next bit. I want us to start thinking about the conversion questions. So conversion questions are like the reaction scheme questions without the scaffold, is the easiest way I can describe it. So instead of giving you guys a flow chart with all the little bits and pieces and with some hints here and there, they just give you 2 molecules and they're saying, go from this one to that one. So you're basically making the reaction scheme from scratch. Okay? So the reason why I wanted you guys to do those 2 molecules is because this was actually the 2021 exam question. They asked you to create a reaction scheme to convert propan into ethylpropanoate, which you guys have seen on the reaction schemes. So this is, like I said, a reaction scheme without the scaffold. When you do that, you need to explain each step. With each step, you need to explain what reagents you need, what conditions you need, and then the products of each step as well. I will go through and show you an example. Julia's giving me a face because she already hates this, I can tell. I will go through and show you an example before I let you guys loose on these questions, just so you can see the overall of what you're trying to do. Does that sound good? I figure you guys probably want an example instead of me just letting you guys try to do pre-learning. All right, let me check in with those that are doing ocean acidification to make sure they have a goal. If you guys want, you can have a think about how you might get from one spot to another, but I will give you notes. Okay? All right, we ready? Good. Get your reaction schemes out, get your notes out, get your flashcards out. It's going to help you. But remember, you're eventually going to have to say goodbye to that and have to do it from your memory. Okay? But for right now, since you are learning, it is fine that you have those out. Okay. So, in this question, they want us to get from the ketone to the ester. So let me just go here. So we are trying to get from this guy to this guy down here. All right? This guy to that guy. That is what the question's stating us to do. Okay? So we got to think of the ways that we do that. You can work on this forward, you can work on this backwards, or you can work on it in both other directions until they meet in the middle. Okay? You got a lot of options. So what I'm going to do on my piece of paper is I'm going to write the initial product down here, the ketone. And I'm also going to write the final product down at the end that I'm trying to figure out. And I'm probably going to put the carboxylic acid on the same side because I like it that way. Okay. So we are going to an ester. And we are starting with a ketone. And we got to figure out how do we get from one spot to another. Personally, the way that I would start tackling this is I would actually start at the bottom and think, what do I need to get to this ester component? All right? Are we okay so far? So if I was to break up this ester into its two components, I would need a carboxylic acid, CH3CH2 C double bond O OH as 1/2 to make my ester, and then the other half to make my ester will be an alcohol. Are we okay with how I got to that step? No. Okay. Here's my ester. The ester is made up of two things. It breaks right here. When it breaks there, I have a carboxylic acid. So you see C double bond O, C double bond O, CH2, CH3. And then I add the OH because that's the carboxylic acid. So that's coming from that half. On this half here, I have CH3, CH2, and then the O from that case is coming from the alcohol. So in order to combine these two things together, what gets removed is the hydrogen from the alcohol and the OH from the carboxylic acid. So those two things get removed and the byproduct is water. So H plus and OH minus are removed, and that makes H2O as a byproduct. And that's how I'm able to join those two organic molecules together. So you got to work backwards. Are we okay with how I did that? She got that okay? Oh yeah, I understand if you're trying to write it down. I'm just making sure you understand it. Okay. Esther? Kind of? All right. Esther. All right. With the ester, this is the functional group that we're looking specifically for. A C double bond O with a single bonded oxygen. Yeah? When I break it apart, I am breaking it from the carbonyl carbon that is single bonded to the oxygen, right down the center here. When I break it in half, I have this half here that's come from my carboxylic acid, and this half here that's come from my alcohol. In order to join those two things together, I have taken out the OH from the carboxylic acid, and I've taken off the H from the alcohol. So that way this carbon bonds with that oxygen. Are we good? Okay, good. Looks like a little bit more relief now, okay? Water gets removed as a byproduct. So we call this a condensation reaction because it makes water in it. All right, something to keep in mind though is that all these reactions want us to label what we need as a reagent. So we got to look at our resource sheet that we're using for now, but we do have to have this memorized. And we are looking for esters as the product. Where are you, ester? That's amide, carboxylic acid. Higher? The brown ones? Yes. All right, so we have it here. Alcohol to ester or carboxylic to ester. What you'll need is the other half plus concentrated sulfuric acid, and it is a condensation reaction. Neither or is the right option, because you see, if you have the alcohol, then you're going to need a carboxylic acid. If you have the carboxylic acid, then you need the alcohol. So for that reaction to occur, the substance I need is concentrated sulfuric acid. And when we classify that as a condensation reaction. Are we good? Are we okay with how I got to that point? Yes? Okay. Can I give you the next point? You're ready. I know you're ready. I'm checking for everyone else. Shika, are we ready? Okay. So, looking at these two organic molecules, I gotta think how one of them comes from this guy over here. All right, because these two molecules did not appear out of nowhere. One of these two needs to come from the ketone that I have up here. Now, nothing in the reaction scheme that I've given you has taught you how to break up the organic molecule by number of carbons. So this one has 2, that one has 3. So if I'm looking back at my ketone, which is 3, is the ketone going to make the carboxylic acid or the ketone going to make the alcohol? There's nothing. This is the carboxylic acid. Because I haven't taught you any way of how to add extra carbons or remove carbons. Yeah? So, since we can't change the carbon number, I must be figuring out a way to convert the ketone into this carboxylic acid. So that's how I'm getting to the next point in my thought process. So we are trying to get from ketone all the way down to carboxylic acid. All right? That's the link. So we're trying to go ketone to carboxylic acid. All right? We have a major problem though, and that major problem is the carbonyls on carbon number 2 in this case, whereas this case, the carbonyls on carbon number 1. You see what I'm saying is the issue. So, C double bond O is on carbon number 2, and we need to move it to carbon number 3, or 1, however you want to think about it. Basically the N carbon. All right? So we got to figure out how to do that. Now, at this point, there are 2 different ways you can do it. I would actually think going backwards still, because I think that's easier, but you could also still go forward if you want. I would think about, okay, if I have a carboxylic acid, what do I need before that to make a carboxylic acid? So what would I need before that? An alcohol? Which type of alcohol? A primary alcohol. The other option is an aldehyde. So we want to break it down to all steps. We could include the aldehyde, or we can bypass it. So let's just do the aldehyde so we make sure we're reviewing all these steps. So we have CH3, CH2, C double bond O, H. That is my aldehyde. If I wanted to go from an aldehyde to a carboxylic acid, what would I need? Alcohol. Not alcohol. Oxidant. Any oxidant will do. You can use Tollens, you can use Flemings, you can use dichromate. That would get me from aldehyde to ketone. Aldehyde to carboxylic acid. Okay. Are we okay with how I did that step? Are we okay with how I did that step? Yes? Yes? Okay. If I want to make an aldehyde, what do I need before that? Alcohol. That is a primary. So again, just work backwards. You're allowed to do this in any order. Again, what do I need? All right, down this is oxidation. Any oxidant as well. I don't know why. My brain likes dichromate because it's orange. So again, another oxidation reaction. Now, just be mindful, we will have another lesson on this, but if I wanted to go from alcohol to aldehyde and just make the aldehyde, we would need to use distillation. If you want to go from aldehyde to carboxylic acid, you would use reflux. We will talk about what these techniques are later. You could also bypass all of this and do like a big bunny hop. You could go straight from an alcohol primary to the carboxylic acid as well. You just use dichromate and you would use reflux. So that also works. We'll talk about that in a later lesson. Don't stress about this now. The main thing I just want you guys to make sure you understand is that to backtrack from the alcohol going backwards. Are we okay with that? Chica, you're looking confused. Where do we want me to start back up? It's okay. All right. You just need to learn the steps. I can show you on the flow chart where I'm going, which is sideways. Can I open this in a way that's not sideways? Edit PDF, what is it? I think I have to too. That's how I did it last time, isn't it? Download. All right, let me just open up the document so you guys can see where, yes, you were right. Is that the right way around? No. Yes, it was. Yeah. All right, just to show you guys where my thought process is going. Here is, where's the esters? Here we go. Esters down here. Yeah? If I want to make an ester, there's two different ways I can do it. One way I can do it is by making a carboxylic acid, which is this guy over here, and adding an alcohol. So if I do alcohol plus carboxylic acid and I go down this route, I get to ester. Are we okay with that? All right. To make a carboxylic acid, I need an aldehyde, which is why I'm going backwards in that step. Aldehyde to carboxylic acid. And then to make an aldehyde, I need an alcohol. So alcohol to, alcohol to to aldehyde. So that's how I'm getting those steps. I'm just following this flow chart. And I have it like semi-memorized. So, all right, are we okay with that one? Okay. So the next big question is, I have a ketone, and this is on carbon number 2. I want to move this so that way there's an alcohol on carbon number 1. So we need to think about, how do I move this? So this is the biggest, trickiest step. First thing I want to do is I want to undo the ketone, so I go back to an alcohol. That would be my first step. Because there's no point in me having a ketone, because when I look at the flow chart, ketone's right here. It's a dead end on my flow chart. So there's no way I can go anywhere with that ketone. I need to undo it and go to the alcohol. Because once I go to the alcohol, then I have a chance of making something. Okay? So that's what I'm going to do for my first step. I'm trying to find more colors, but I feel like I'm going to run out of colors. So ketone, if I want to undo that, it would make a secondary alcohol. Like that. In order for me to do that reverse reaction, I need to think about my reagents. So let's have a look at our sheet over here. We are going from a ketone to an alcohol. Yeah, I think so. Just want to make sure I get the right ratios. Here we go. Ketone to secondary alcohol. NaBH4, and that's a reduction reaction. Reduction. Okay? All right. So now I have a problem. This is a secondary alcohol. This is a primary alcohol, so I need to move it. Now, when we look at the flow chart, there's no direct way to move from primary and secondary. You see? So the trick here is to go backwards to an alkene. And let me show you why we do that. Bahar's already got it. All right, so first off, I'm going to go backwards to an alkene, so that way I can actually move things around. So going to alkenes helps you shift things down the carbon chain. Just trying to find a color I haven't used yet. I feel like I should all of them. All right, so if I was to do this, and I was to make an alkene, I would take the OH off, and I would have to take a hydrogen off from a neighboring carbon. Doesn't matter which neighboring carbon I take it off of. No, because either way, the double bond's still forming between carbon 1 and 2. So we have CH2 double bond CH, CH3. Now for me to go from that to that, let's see what reagent I need. So we're going from an alcohol to an alkene, concentrated sulfuric acid again. And that is an elimination reaction. I'm not doing that. All right. Are we okay with that? Cool. Then we're going to undo that step, and we are going to be doing an addition reaction. Because when I do that addition reaction, guess what? The alcohol can go on carbon number 1 or it can go on carbon number 2. So, let's see what that is. So when I do this addition reaction, I haven't used yellow yet. I'm going to break this double bond, and I'm going to be able to add an OH. The major product is going to add the OH to carbon number 2. Because when I break this double bond here, I have two options. You break the double bond and you add the OH either to carbon number 1 or carbon number 2. In this case, this is the rich carbon. That is the poor carbon. So if it adds it to carbon number 2 on the poor carbon, that is my minor product, which is what we had back here. So if I went backwards that way, that's my minor. If I go and I add the OH to, no, sorry, that's the major. Yeah, that one's major. Oh, yes, that one's major. So that's the major product if I went that way. If I go this way, that's the minor product. So the OH gets added to carbon number 1 instead. So that's how I get there. So in this case, we are using Markovnikov's rule. The rich get richer. So I break this double bond, and I'm trying to figure out where the OH is going to go. If it goes onto carbon number 1, I have the minor product. If it goes onto carbon number 2, it's the major product. Because remember, when you're doing your addition, you have the hydrogen ion, the hydrogen and the OH. So let's double check what we need for reagent-wise. It looks like it's just acidified water and heat. So all you would need is H2O, and with heat. And you want to take the minor of that product. And then you go step it. And that's how you get from one spot to another. So the trick then in this case, in order to move something down the carbon chain, you probably need to go back to an alkene. So I'll write that as a note. So this bit here, in order to move a functional group down a carbon chain, you need to make an alkene. So it's exactly like the flowchart with no scaffold, which is the unfortunate thing. This is like the harder version of the flowchart. Draw however you want. All right. Marking schedule for this question, I actually don't know off the top of my head because they pulled down all the assessment. Let me see if I can find it. Yeah, so I don't know what's going on because it says there's no files online, and there should be. So I do know that they have changed it so that way there are. They have changed it so they're only putting the 3 most recent. So there's nothing on there. So I think there must be a bug in the system because there's something that's gone down. So NZQA should have all the exams, but they only have the marking schedules for the last 3. I think I've downloaded all of them because I knew they were going to do this.
Oh my god, there's nothing there.
I know. That's why I was irritated. That's why I didn't give you guys the 2023 question.
You know, someone was talking about changing to my bioexternals.
Yeah.
I was trying to look for the human evolution one and couldn't find it until 2030.
The questions? All right. This was question, I want to say... question 2C. Okay. I'm just looking at the marking schedule online. So here's how the points broke down for this. Okay. Make sure there's all of it. Okay. So, is it frozen still? Oh, there we go. Yeah. Okay. So this whole reaction scheme, if you could do that and answer that, that is excellence. So I don't want you to freak out if you don't understand this yet, because I've given you guys an excellence level answer. Okay? The good news is, just doing this, no extra writing, excellence point. So this is what I'm saying about organic. Like, easier to get the excellence on, harder to get the achieved on. Because this here, no writing involved, just figuring out how you go from one place to another. So long as you have that flowchart memorized and all the reagents memorized, you can put this together, no problem. All right?
But that doesn't,
It's excellence. You don't have to justify anything. That's why I'm saying organic is nice like that, in a sense that so long as you can do the process, you're fine. So, but when I say the excellence point, I'm referring to you need to have all the reagents. You need to have all the products. You need to mention that you're taking the minor product here. How is that even possible? That's it. All right?
Did you have them all memorized at one point?
I don't think so. Oh, next time I want to test on this. It's just not that you can memorize them. You do it enough times, you're like, I feel like my brain's gonna recall some stuff already. Yeah. All right. The merit, everybody. Oh, boys. The merit is 3 correct steps or correct pathway with minor omission. So 3 correct steps could be 1, 2, 3. 3 correct steps. So if you are not sure how to tackle this problem, get it started at least. And it doesn't have to be 3 connecting steps. You could say, I couldn't figure out this bit here. Maybe you forgot to do that, or you didn't know how to do that. You wrote this conversion, and you understand I need to do these steps to get to a carboxylic acid to get to my ester. So you forgot how to, you don't know this bit. You get a merit. Okay? The other way is you have the whole flow chart, but you forgot something. So say, for example, you forgot a reagent. All right? Not very forgiving in that sense. So do give the questions a go. Do try it, because there's usually little points in there. And that's, again, the challenging thing about organic, and that's why I say it's hard to get the achieved on this, because you need to just take a bite at it and do it. All right, for the achieved was that recognizes that reduction is required in the first step, so you knew you had to undo this. That was an achieved point. The other achieved point is knowing that the ester is made up of these 2 molecules. So if you had nothing in the middle, but you could figure out the last step and the first step, you got an achieved point for each one of those. So that's why I'm saying just start it. Even if you don't know how to get from one to the other, just do at least one reaction conversion. Okay? That's the conversions. So it's just like the reaction schemes, but no scaffold. All right? Questions, concerns, comments? No? All right. Hopefully my computer's going to be open this up again, because it's been crashing a lot. All right, we've done our conversions. So let me explain. Do you guys want another lesson on this, I'm thinking? Yeah? Okay. So what I'll do is for Friday, I'll give you guys basically a study lesson like you did the other day. I have a CPR quiz, but I'm not printing it off, because this question you really don't have to print off, because it's just convert from one to another. So I just got to tell you what the 2 molecules are. Your choice how you want to use the remaining, what is it? 25 minutes of class. Here's the Mahi choices. Again, don't spend all the time just trying to memorize your flashcards. Maybe do it once, go do something else, and then come back to it and see what you can recall. The thing is, while you guys are doing these practice questions, you're accessing that information anyway, because you have to memorize it. You can do the summary flow chart and make some notes on there. You can do the SciPad pages, which I listed on Google Classroom. You can work on the no brain too small collated questions, or I'm happy if you want to do the CPR question as well. And I realized yesterday that I didn't hand out CPR quiz number 3, so I'll do that as well. All right. Choose what you want to do, and then when I see you guys on Friday, it'll just be another day of just working like this, and I'm happy to do another example on Friday too.